All right. Welcome, everyone. Thank you, guys. Thank you all for joining us in the third and the April MES monthly meeting. It's very exciting. We usually do a rotation between a hands-on tutorial, an early career seminar, and then an expert panel. We usually do those in a tri-monthly rotation, but for this month, we are fortunate that we kind of flip them. So stay tuned for the expert panel. That'll be coming up. That'll be released. The information about that will be released in the next few days. But otherwise, if you're interested in joining the MES Society, if you're not a member already, please go ahead and scan this QR code or follow this tiny URL to become an MES member. And then also, if you are an early career researcher and you want to present, please sign up on this Google form. Or if you want to nominate someone, let us know also. And then if you want to be featured in the newsletter content, please use this QR code right here. And then we're also always looking for ideas on what to implement. So without further ado, I'll drop these links also in the chat in a bit. But without further ado, today we're going to be focusing on PyPSA. Trevor is going to be talking to us about it, and we are really excited to be hearing in from him. This is meant to be an interactive workshop, so I'll let Trevor let us know his expectations on that, but we're very excited to hear from him.
Beautiful. Thank you. Yeah, let me share here and we can get started. So hopefully you can see that okay. My name is Trevor. I'm a PhD student at Simon Fraser University in Vancouver. And together with Kamran Taranchi from Stanford, we have developed PyPSA-USA for the last few years. And now recently there's been a few more people jumping onto the development team. So we figured it'd be a good time to do a presentation about it. Unfortunately, Kamran is out sick today, so I'm taking on his part of the presentation. He has done a lot of development on the power sector side, which will be the first half of this presentation. And then I've done a bunch of development on the multi-sector side, which will be the second half. However, together we've been working together in the same model. So a lot of it is a lot of the shared code base. In terms of presentation format, feel free to raise your hand or just interrupt me throughout if there's any questions. But without further ado, I guess I will get started. So yeah, PyPSA-USA, it's a flexible and open source electricity system planning model for the USA. And again, for the first half, I'll focus on the electricity side of things. So what is PyPSA-USA? It's a data model and optimization tool with flexible transmission resolution and a broad temporal scope. So what does that really mean? So we use PyPSA, which is the Energy System Optimization Framework, and that is developed by the team at TU Berlin in Germany. And it's a very reputable tool. It's open source and is used for a lot of different projects. We have created a USA variant of that. So what that is we've just compiled a workflow around a bunch of USA data from a bunch of these sources you see on the left-hand side, such as the EIA and EPA and NREL and Puddle and all these different sources. So we created a workflow to compile all this data and we pump it into the PyPSA framework. At that point, we have a data model that you can either run on PyPSA itself, so use the underlying PyPSA optimization engine to do energy planning studies, or you can use this data model to run your own optimizations on. So maybe you have your own optimization framework. You can use PyPSA-USA to generate the data model and pump that into your own framework. And then on the right-hand side there, we have kind of the more graphical abstract of PyPSA-USA, if you will. And we'll get into all the data and how we arrive at this transmission network. Yeah, that's kind of like the high-level overview of what PyPSA-USA is. It's a data model and optimization tool that's tailored to the USA with configurable resolutions. So first up, what do I mean by configurable resolutions? So there's kind of three big dimensions we look at. We'll look at the spatial dimension, the temporal dimension, and the technological dimension in this presentation. So first up, the spatial dimension. So when we ingest a network, on the very far left-hand side there, you'll see maybe it'll come in as a nodal network where it's very spatially disaggregated. However, oftentimes you have to do spatial clustering on this to make these networks computationally tractable. So PyPSA has a lot of nice to have features. So you can kind of take this nodal network that you see on the left-hand side, and you can cluster it into more of a zonal network that you see in the center. And you have options where you can cluster maybe the transmission capacity, so those black arrows going between these zones, but you can keep individual assets within each zone separate to capture different things like renewable potential profiles within each zone separate. Or you can go further and cluster assets together, kind of showing the far right-hand side photo there, where you're clustering everything within the zone together. So there's lots of different ways you can do spatial clustering. And since we're building on the PyPSA framework, which has a lot of these tools built in, we can take advantage of that very easy. So in the spatial dimension, that's kind of the high-level overview of clustering. And then in the temporal resolution, on the top here, we have kind of how you can slice the temporal dimension. So what I mean by that is on the top, maybe you want to do something like representative days where you only model individual days throughout the year. So maybe this is kind of like peak demand or extreme events. Or maybe kind of in the center top, maybe you want to implement some sort of resampling or clustering to still capture average days and this kind of thing without having to model every individual hour. Or maybe you want to do like full chronological on the bottom where you model every single hour of the year. These are all very configurable parameters within PyPSA-USA. Moreover, on the bottom here, you can model different time horizons as well. So maybe you want to model for 2030. You can do that. You can also do that for 2040 and 2050 in a single model. And you can do that with different types of planning decisions as well. So maybe you want to do a perfect foresight model where you can see the decisions you're going to make for 2030, 40, and 50 all at once. Or you can do this with myopic implementations. So you make decisions and run your model for 2030, and you pass those decisions into a 2040 model, and you pass those decisions in a 2050 model. So there's lots of different spatial and temporal options you have with PyPSA-USA. We have two big networks that you can use in PyPSA-USA. One is a nodal network, and then there's a few different options for zonal networks. So first up, for our nodal network, we take a synthetic network from Texas A&M University, shown on the left-hand side there. So it's a synthetic network of the USA. It has about 80,000 buses and 100-ish thousand lines. And we can implement that right into PyPSA, shown on the right-hand side there. In this translation, we bring over full AC parameters as well. So if you want to do some power flow studies, you have that option as well. Or you can do the clustering techniques we talked about on the previous slide to cluster this down to any set of nodes you want. So for example, you can take this nodal network on the left-hand side, you can show where you maybe want to cluster the WEC region into 100-ish buses. You can do that very easily. Or maybe you don't need that type of resolution. And on the right-hand side, you can model with only like 5 or 10 or 20 buses to keep your computational burden lower while still capturing the details you want. So there's lots of different options you have with your spatial resolution and clustering. In addition to the nodal network, we also have 3 different zonal networks we pull in. So starting on the right-hand side and moving left from least resolution to highest resolution, we have the FERC 1000 planning regions, and then we have the Reed's Balancing Authority regions, which have about 130 zones for the USA. And then the left-hand side, we have county-level regions, which is about 3,000. So these zones, the transmission limits between these zones, they are based on nearest n-1 derived transmission networks. So they're based on very realistic data. However, they are zonal networks. So these are very suitable for planning studies where you want reasonable estimates of these actual transfer capacities between zones. and when still running at a zonal network is okay. So again, PyPSA-USA, you can choose whatever you want. So maybe you wanted to do a nodal network of WEC, you can do that. Maybe you wanted to do a zonal network of just a certain amount of states, you can do that. So all these options are very user configurable. And in the second half of the presentation, we'll go over a little bit more kind of concrete example of that as well. Yeah, that is the network representation. Once you choose your network representation, then you have to start populating your model, with a bunch of different demand parameters, or a bunch of different parameters in general. So first up, we'll talk about demand. So demand, you have two options. One, you can use historical demand. This comes from EAA 930 directly, and this comes in at balancing authority level. If you run at a resolution higher than balancing authority level, for this, we'll just do population-based disaggregation for your load. Or if you're doing a future demand, we pull in data from the NREL or NLR, I guess now, electrification future study, and this will give electrical hourly state level electrical demand profiles for 2030, 2040, and 2050. So you can pull those profiles in directly, and if you choose a year between those, like 2035, we'll just interpolate between them. And again, this is all configurable as well, and there's all automated. So in a configuration file, which we'll look at the end, you just type in what you want, and this will all get pulled for you directly and pumped into the PyPSA model. Next up is the generator data. So a lot of this data comes from EIA via the Public Utility Data Liberation Project. And a lot of this data is like asset level, nameplate capacity, heat rates, seasonal deratings, operation maintenance costs, fuel costs, emission rates, capital costs. We have like locational multipliers for locational costs, or for capital costs, sorry. So behind the scenes as well, we bring in a lot of techno-economic data at the highest resolution we can get. A lot of times for like fuel curves, that might be like state level wholesale prices, or sometimes we can bring these in at and use like fuel rates and heat rate, or fuel prices and heat rates at an asset level to derive some prices as well. So it's really dependent on what data is to what resolution we get, but in general, via Puddle, we can get fairly high resolution data. For renewable potentials, there's two different paths we can take. So one is using ERA5, that's climate resample data from the past 80 historical years. And we use AtLight, which is a package developed by the PyPSA team for processing renewable energy potentials. And ERA5 comes in about like a 30 by 30 kilometer grid, and that allows us to get both solar and wind profiles, and we base those on historical years. So this allows us to choose different historical years to kind of stress test your model. So maybe you want to choose a year that you know had either like low or high wind or solar potential to see how your model responds to that. Additionally, the Pacific Northwest National Labs Go Deep Climate Dataset that was just recently integrated. So that has historical data from 1980 through 2022, and then future climate scenarios as well from 2022 to 2099. And I think that comes in a little bit higher resolution, and it has different RCP scenarios. Yeah, so that's renewable generator data. In addition to renewable generator data, when you're making investment decisions, you want to, especially for like wind and solar, you want to make sure you constrain it based on land use availability. So we pull in a bunch of data in terms of exclusion areas on where you can actually invest in different amounts of wind and solar to give better estimates of what your actual upper bound potential is. And this is in addition to like build rates and stuff as well. So we do bring in exclusion zones. Yeah, it's renewable technology potential. once we bring all this data together, we can formulate it as our optimization problem. And in general, it's just a cost optimization. So we take our operations cost, we take our investment costs, and we try to minimize that. And that's subject to generator operational limits. So this can be things like ramping constraints, minimum up and down times, these kind of things. We also have unit commitment in there if your research question demands that. Land use constraints, so again, looking at those kind of exclusion zones, storage power, and energy constraints. So, sorry, I got lost here for a second. Yeah, storage power and energy constraints. So, nameplate capacities and this kind of stuff. Transmission limits. So, again, these like zonal interface limits or the actual nodal connections, your transmission capacity limits, power balance constraints, and policy constraints. Policy constraints is definitely the most room for user configuration on different research questions. So they can be things like regional mission limits, capacity targets, portfolio standards, planning and operational reserve margins. And you can really tune these a lot to see how your model responds to different policies, which can give new insights on investment pathways. So once you've formulated the model, then you have to actually run the model. This can be a very daunting step. We've tried to make it as easy as possible. So on GitHub, you can go to the PyPSA-USA GitHub, and it'll take you to a documentation site. It'll walk through how to do the installation of PyPSA-USA, and then how to actually set up the model and do everything we talked about. There's a bunch of config files in the repository. They'll walk through all the different options you have. Moreover, we've tried to make it, again, as easy as possible on the documentation site where we outline what all the different configuration options do. So once you get to this point, you've decided your spatial, temporal, technological dimension resolutions required. You set up your config file. You've then run the model. All this data will be pulled in automatically and processed for you into a PyPSA network that will be run and optimized, and then you can view some results. This is just a sample results from some Kamaran's research. So on the left-hand side, kind of the top left, you can get these capacity plots across the USA, and this will show different investment pathways and kind of at a spatial resolution where capacity investment is happening. Down below, you can really drill into individual nodes and see what generation profiles are like, all the way down to hourly resolution. And then on the right-hand side, you can also look at, these are just different capacities for each planning zone Kamaran has laid out. Yeah, so this is just a sample results. That's kind of the big aspects of the power sector side, I would say. I know I went through a lot of the power sector side super quick. Apologies for that. Kamaran, if he was here, he would have done a better job at explaining all the power system side, but I am happy to answer questions of the power sector side before we move on to the sector coupling side as well, because I think that's all I had for the power sector side. Not sure if there are any questions. Oh, I see one. Is Go Deep only for WEC? No, Go Deep will be for the whole USA. So when you, let's just flip back to that slide. I think I have a hidden slide on that as well. So yeah, so Go Deep, this comes from the Pacific Northwest National Lab. And apologies, my knowledge in Go Deep is not super in depth. I have not actually used it myself personally. But so it covers the full USA. I guess from Cameron's picture here, it says temperature at 2-meter resolution. So I guess it's much higher resolution than Error 5, which is kind of a downside of Error 5 when you lock to these 30 by 30 kilometer grids. And one of the big things with Go Deep is I know it has future scenarios where it takes into account global warming. So this allows you to, again, like stress test your model if like at a in a scenario where you have a higher degree of global warming versus a lower degree, how does this actually impact your wind profiles and your solar irradiation and these kind of things? Yeah, let's go deep. Yeah, that is all I really had on the power sector side. I know, again, this was a lot. I'm sorry, I probably went through it kind of fast. But on the sector coupling side, we'll go through a more of a concrete example as well, which I hope will solidify a lot of this kind of abstract workflow concepts a little bit better. Yeah, so since I don't hear any questions, I guess I will jump into that now. Okay, perfect. PyPSA-USA sector. So PyPSA-USA can broadly be broken into two sections, the power sector side and then the sector coupling side. The sector coupling side builds totally on top of the power sector side. So what I mean by that is in the PyPSA-USA, what we just talked about was the power sector. So very broadly, you have renewables, fossil fuels, they go into some zone or node that has a power sector demand attached to it. And then you look at things like what are your generator investments and generator dispatch decisions on these power generators. Sector coupling takes a single electrical demand that you'd have attached at a node, and then it breaks it down into 4 separate demands. So we'll have a demand for residential, commercial, industrial, and transport. And then we will build in connections from our fossil fuel sources as well that can go into each of these sectors. And we'll add in more demands. So for example, in the residential sector, we'll have electrical, heating, and cooling demand. We'll have the same for commercial, industrial, and transport. And then these demands can be met via electricity or fossil fuel directly and across a wider array of technologies. The advantage of this is you can get more explicit insights onto how different sectors are going to evolve throughout the energy transition. The downside of this is that it adds a lot of overhead to your models. So you have to be more careful on your resolution choices for all of your spatial, temporal, and technological dimensions. Moreover, in PyPSA-USA, we have also added in a natural gas module. So this allows us to track natural gas at a state level and look at different pathways with natural gas as well. So how much natural gas is being used, what happens if we increase or decrease the supply of it, and these kind of things. So I thought the best way to go through sector coupling would just be to do a case study on it. So we'll do a super simple case study. So we'll have this very vague research question of we are going to evaluate regional decarbonization pathways in New England for 2030. So we're going to pick a near-term target. And we just want to look at maybe state-level decarbonization pathways. Since we're going to look at a near-term target, we probably want to look at a multi-sector analysis because for a lot of electrical solutions, these are supply-side solutions, and they'll take much longer than next 5 years or so. So we want to look at individual sector demands. Since the near-term target, we want to do a brownfield expansion. So we're going to look at our end-use technologies and ensure we capture how much technology is currently in the system on both the supply side and the demand side. And then we're going to look at how different fuel and policy limits impact our decarbonization pathway. The specific metrics we're going to look at are then going to be emissions, energy flows, and system costs. So this is our vague research question, and luckily PyPSA-USA is able to answer these questions for us, which is super. So the first thing we want to do is we want to set up our spatial and temporal scope. So on the right-hand side, this is New England. This is the region we want to model. So then in our config file, in GitHub, which will walk you through it, this is just a portion we'll see here. The first thing we're going to do is we're going to set our interconnect. So PyPSA-USA is broadly broken into 3 interconnects, the Eastern, Western, and ERCOT, so Texas. We are in the Eastern interconnect. So we are going to look at that. The next thing we're going to do is we are going to model each state individually. So we're going to have 6 zones, so 1 for each state. This will be the number of clusters. And then the simple wildcard will say the number of renewable potential zones. And I have a slide on the next, or a picture in the next slide that'll demonstrate what this 120 really looks like. Next up, we will then set these options and our planning horizon. So we know our planning horizon will be 2030, so we'll set that there. If we're doing multi-sector, then we'd add multiples here, so it'd be 2030, 2040, 2050. Since we're only doing 2030, we'll leave it as that. Our options, 1 hour, so we're going to run at hourly resolution. And then the TCT there is our technology capacity target. And this will just bring in a policy constraint limiting how much capacity each technology can be installed. And we'll look at that later on. We will enable a sector coupling study by setting the sector value to G. It's kind of a long story why it's G. Just in the short term, just put a G there and it'll enable sector coupling. That's on the to-do list to make a little bit more clear. And then our model topology, we are going to use Reed's zonal limits. So from the previous presentation, that would be that middle network where there's about 130 zones represented. And then the zones kind of perfectly match up in this case with the state level boundaries. And then our 6 states for New England. So Maine, Massachusetts, Vermont, New Hampshire, Connecticut, and Rhode Island. That's all you have to do for the spatial and temporal resolution setup. So it's pretty straightforward. And the documentation site kind of walks through what each of these does a little bit more clearly as well. So the simple wildcard, what that did, it allowed us to have 120 renewable potential zones. And that's shown on these slides here. So the left-hand side is our solar capacity, and the right-hand side is our wind capacity. So what this allows us to do is within each state, we're going to have more than one solar generator and more than one wind generator. So this allows us to catch different renewable potential profiles within the state. So unlike natural gas, for example, which we might just have as one generator for the whole state or for each node, since we want to capture different renewable profiles depending on where in the state you're located, this allows us to do it. So it's just a way to capture more detail with different renewable potential profiles. Once we have set our spatial and temporal resolution, the next thing we're going to do is look at our demand. Unlike the power sector demand, we're a little bit more locked in on what we can do in the multi-sector side. So in the configuration file, there is a section to configure demand. Well, we're going to walk through for each sector how to set it up, but we are more limited. So for example, in the surface sector, we don't actually use anything in the configuration file. We just pull directly from NREL's ResStock and ComStock data sets. And this gives us hourly load profiles for all of space heating, space cooling, water heating, and electricity for both residential and commercial. And that's shown on the right-hand side there. So we pull this data in directly at a state level, and then we'll apply some desegregation methods to that, as we'll talk about in a second. But from the config file, we don't actually use any of the options there. This just highlights that this data set pulls in both the profile and the magnitude as well. So on the left-hand side, you can see the different magnitudes across the New England region. So Massachusetts has the biggest kind of total load compared to Maine and Rhode Island. Moreover, on the right-hand side, this just shows for each region, there are different profiles as well. They kind of look similar, but they are different. So that's the ResStock and ComStock data set. We pull those in directly. Yeah. Next up is transportation. So transportation, we do use profiles from this demand configuration, and this will be the electrification future study again. Um, and the configuration options we use for that is EFS case and EFS speed. So the electrification future study, it gives 9 different scenarios for future electrification options. So EFS case would be kind of a low, a reference, and a high, I think. So this is how much electrification adoption will happen. And then the speed is how fast it happens. So it's like low, moderate, and fast, I think. So if you want to look at maybe like a fast electrification, you would put in an EFS case, maybe high, so you get a high adoption, and that adoption comes very quickly. And this gives us profiles for our light duty transport up top, then our top left, our medium duty top right, heavy duty bottom left, and buses bottom right. And these profiles would change again per each EFS case and EFS speed you choose, but also for the year as well. So if you choose a planning horizon for 2030, these might be the profiles you get. But if you choose one for 2050, we'll pull in the 2050 profiles from EFS automatically. Yeah, so that is where our demand profiles for electric vehicles come from. And then our demand profiles for the industrial sector, this one is a little bit more having to splice things together, since industrial profiles are notoriously hard to track down. But what we do is we use a study from NLR that will give yearly emissions by fuel. We benchmark that against the EIA Manufacturing Energy Consumption Survey, and this gives us yearly loads at a county level that are calibrated against the EIA consumption survey. And then we apply profiles to that from EPRI. So they give approximate load shape profiles for like heating and electrical. And we'll talk a little bit more about industrial representation later on as well. Similarly, in our config file, we don't actually use any of the parameters in there. You are locked into this situation or this kind of methodology right now. You're free to go and change it. However, just based on kind of data restrictions, there's not too many options that we have available right now. So once you have all your demands, if we are running at a higher resolution than state level, then we have to disaggregate our demand. If we're doing residential, commercial, or transport, that's just based on urbanization ratios, so population-based disaggregation, and that's same as power sector as talked about before. And that's shown in the right-hand side there, so we just pull in census data. If you are doing the industrial sector, then we pull in disaggregation based on emissions. So from a NLR emission study, we'll disaggregate the industrial load throughout the state following this emission study. Yeah, so we do try to capture like spatial impacts of industrial demand. Yeah.
Could I actually jump in with a question here?
Yeah, please, please.
Yeah. So I know that you can disaggregate between like different types of residential, commercial, or transport stock, but it seems like industrial seems a lot harder. So are you not able to do like different industry sources of demand?
Yeah, that's a super question. We don't have data to be able to break down right now. So for example, we'll talk about in a bit, like how we just have one heating demand. Like we don't break it down by like low temperature heat demand, high temperature heat demand, or like if it's for the concrete sector or chemical sector, these kind of things. So right now it's just kind of a singular industrial demand that's grouped together, and then we just disaggregate based on the single emissions data sets. Yeah, and it's basically just like data restrictions is kind of what we're working with right now. PyPSA Europe, their project is a lot more mature than PyPSA USA, and they've put a lot of work into the industrial sector, but it's been like a lot of like manual work on their side. So like just going and kind of hunting data sets and do manual mapping. So it's kind of like on the to-do list for PyPSA USA, but just getting like the research project to support that is needs to happen still. Yeah, thank you for the question. It was good.
Trevor, can I jump in with a
Yes,
question also?
yes, please.
You keep mentioning like different data sets that are inputs, especially from the national labs, and obviously those are usually open source. Um, if does PyPSA change anything in those, or does, for example, if you feed in an updated, for I don't know, CSV file from NRL or whatnot, would do you have to change anything else for PyPSA to work, or would it be ready to go right off the bat?
Yeah, that's a great question. Thank you. So, um, if you don't implement any sort of policies, which we'll talk about kind of later on, it'll work right off the bat. And so by policy, I mean like our technology capacity constraints. So if you want to limit how much solar can be installed, that'd be like a input you would normally put. But if you don't include any in that, all the base information such as like power plants, loads, these kind of things, they all come in automatically and you don't have to touch anything. The only kind of interaction you'd have to do would be when you want to start kind of modifying different policies to see how this changes your investment and dispatch decisions. Yeah, and we'll go over like where those files are in a second as well. Yeah.
Gotcha.
Yeah, thank
Can
you for
I
the
jump in
question.
with another question?
Please, this is super.
Going back to the residential demand. So in the transport, you talked about the EFS profiles.
Yes.
In the residential demand, are those EFS profiles included for, like home electrification and stuff like that, or do you just pull the base res stock from the 2018 runs?
Yeah, so this is just so Restock and Comstock, they are tied to the 2018 weather year, which is a little bit of a downside with the sector coupling right now. So these are tied to one specific year, and then in a slide we'll get to in a second, we have methods to scale this data to 2030 or 2040 or 2050. So unlike EFS, which will directly give us these 2030 magnitudes, we will scale these profiles to estimate what the actual magnitude should be at 2030 or 2040.
So when you do that, are you assuming like 5% heat pump adoption or something like that? Or are you just taking today's numbers and increasing demand for future?
We don't assume any sort of specific technological adoption. We will just assume this like end use demand, and then maybe it's a good point to just skip to the slide right here. And then, oops, sorry. We will take energy outlooks, so EIA's energy outlook, which will give like final end use demand and scale it according to that. So we'll say space heat will have to grow from, I don't know, like 9.0 to 9.4 over 2030, figure out what that multiplier is, and just multiply our space heat and electrical demand by that multiplier. And then PyPSA-USA will decide if you should meet this end use space heat demand via natural gas furnaces or heat pumps or what have you.
Oh, interesting. Okay, thank you.
Yeah, that was a good question. Thank you for that. Yeah, and that kind of leads us into this scaling load profiles. So when you choose a specific profile, so in the config file, you can select this AEO, so annual energy outlook, and you can choose any one of their cases. So shown on the right hand here is the AEO's commercial load energy growth. And there's, I think, like 15 or 17 different cases here. I just show 6, I guess. So you could say, I want to scale my demand according to the high economic growth case. And it would take the magnitudes or the profiles of your base year and then scale it according to that. So for example, the Restock and Comstock, which are tied to the 2018 weather year, we would go and find what the actual energy usage was from 2018 from the EIA and then scale it according to future projections. And this comes in at a sector level. So we have one for commercial, residential, transportation, and industrial sector. Yeah, that is demand. Thank you for those questions. They were really excellent. Next up, once you've selected your demand, you have to meet the demand through different technologies. So first up is the service sector. So in the config file, the first thing you set is your heating set point. And this will generate your coefficient performance profiles for your air source heat pump and your ground source heat pump. So the value put in there is a sink temperature. And then on the right-hand side, these are predetermined or pre-calculated as inputs to the model. So then we'll take actual like ambient temperatures from error 5 or whatever, and we will generate these profiles based on equations from literature. So shown here in the gray lines, maybe the ground source heat pump on the right is a little bit more clear. The gray lines are each state individually, and the blue line is the average for all of New England. So as you can see, like ground source heat pump is a lot more stable and on average a little bit more higher than the air source heat pump, which really takes a hit in the winter months when it gets really cold. However, of course, we have techno-economic parameters in there to show that air source heat pumps are a little bit more cheaper. Moreover, for heat pumps specifically, we also pull in urbanization rates to constrain where ground source heat pumps can be installed. So you can't install ground source heat pumps everywhere if you're in the middle of a city, for example. So that's the heat pumps. So that's the first config option. Next one is then surface sector, the different technologies. There's two main technologies, so one for space heating, one for water heating. For space heating, these include electric, gas, and oil furnaces, and then heat pumps, both ground source and air source, and air conditioners. So heat pumps can obviously meet both heating and cooling demand, while air conditioners can only meet cooling demand. We estimate existing stock from EIA's residential and commercial energy consumption surveys. These are just surveys, so some of the values can be a little bit weird, so user beware, but there are estimates in there for how much existing stock is in the system and lifetime on that existing stock. The true false values here in the config file just say if this technology is allowed to be invested in or not. Existing stock will always come in regardless if it's true or false. And then for water heating, we have electric, gas, and oil water tanks. And these have storage attached to them as well. Since they're I should say they're all they're not instant electric water heaters. They're all assumed to be storage water tanks. And then just to kind of hit home so here we'll set oil water tanks to false, and we'll see in our results at the end that we don't see any investment in it. That is technological representation for the surface sector. Next up is the transport sector. So when you turn the transport sector on, road transportation is always turned on. So this is broken into our 4 units classified before. So light duty, medium duty, heavy duty, and bus demand. This can be met through both electric vehicles and internal combustion engines. And this all ICE vehicles just run on petrol or general gasoline. There's no differentiation between diesel and gas and whatnot. And then on our config file, we pull in dynamic costs. So this will just pull in gasoline cost curves at a monthly and state level from the EIA to get some sort of cost curves that match your historical weather year. EV policy, we'll look at this config file in a second, but this will just dictate how much electric vehicles are allowed to be invested in for each year. Must run EVs. This is just a operation condition for EVs. It's in the docs. I won't go into that. And then there's also in the transportation sector, freight rail, freight air, passenger air, and freight marine domestic shipping. These demands are in the model, and you can turn them on or off. If you turn them on, they're strictly for emission accounting purposes only. There's no decarbonization pathways for them right now. It's set up so you can add decarbonization pathways, such as like sustainable aviation fuel and whatnot. However, the actual implementation that's not in the model. So it's just strictly for emission accounting purposes right now. And existing stock is taken from, estimated from the NLR Electrification Future Study. The industrial sector, it's a little bit more crude. There's only 2 demands to be talked about. So the electrical and heating, and these can be met through gas, coal, or heat pumps. Dynamic costs, again, this will pull in. So for fossil fuels, cost curves from the EIA, historical cost curves. And then since it's so crude, you can usually get these like weird investment decision happening. So there's this min-fossil generation just to enforce a certain amount of fossil fuel generation for the industrial sector. So you don't get like very drastic decarbonization events happening. And then finally, the natural gas sector. So natural gas is represented at the state level. So you can have this state level of natural gas. There, on this natural gas, there's our processing facilities, our underground storage facilities, and then we estimate line pack as well in the natural gas system. We then have connections to other states and connections to outside the model scope as well as boundary conditions. And we'll talk about that in a second. And these all come from the EIA mostly. Yeah. And leading in, so the last thing before we kind of run our model here is our boundary conditions. So the two boundary conditions is our electrical trade and our natural gas trade. So first up is the electrical trade. So in our config file, you turn them on by selecting this imports and exports. So this will just allow imports and exports to areas outside your model scope. The costs, this will dictate how much you cost to import electricity or how much money you make from exporting electricity. So if you set to wholesale, this will just take cost curves from the adjacent states, electrical profile from the EIA again. If you set it to carrier, you can set it to a certain carrier. So you can say, if I'm going to import electricity, just set it to the cost I pay for open cycle gas turbines, for example. Or you can set a specific value as well. So I don't know, $10 per megawatt hour or whatever you want. Volume limits, this is kind of the biggest boundary condition. So volume limits will be how much energy you're allowed to import and export in proportion to your final electrical demand. So what I mean by that is if we set it to 20% here, this will say of my final electrical demand, I'm allowed to import up to 20%, or I can export up to an additional 5%. And then the balancing period is over what time period? So maybe I'll say over the year. So over my total year, if I sum up all my electricity, I can only import 20% of my final electricity. And these values we can go and get from either like an ISO state or page directly or somewhere like Puddle, and just look at historical values. So these are just kind of like upper and lower bounds on how much electricity you're allowed to import and export. And the capacity limits will just say if you have to respect existing transmission capacity to those adjoining states. And then CO2 emissions, if you want to attach CO2 emissions to your imported electricity. Yeah. Natural gas trade is the last boundary condition. So again, natural gas turn on. So our system will look something like this, where we have connections to each state. And then outside of model state to like New York and Quebec, we have these boundary conditions we want to set. So our imports and exports, very similar. This will say in relation to our weather year, how much we're allowed to import and export. So for example, our export will say in relation to our weather year, if it was 2018, we can export up to 1.2 or so, 20 extra or 120% what we actually exported in 2018, or we can export as little as 80% is what we actually exported. The reason these are in here is if they're not, you can run into like very weird situations where your like natural gas values are just way out of whack. Because especially if you just run single states where it's just like a transfer state where it's just like natural gas passing through to a neighboring state, you want to make sure you capture these flows and that like individual state's not using all the natural gas. So it's just in here to enforce some sort of like realistic bounds. Cyclic storage, so if we want to just make sure our storage values start and end at the same location, marginal costs, and pipeline multipliers. So I'm running out of time, so I'm going to go a little bit quicker. And then we have methane as well. So for emission accounting, you can track methane leaks and attach a global warming potential to that as well. And then finally, I know I said before that was the last thing, but I guess I lied because we also have to set up policies. So the two we're going to implement is our technology capacity targets and our EV policy. And this is the point, I think, where if you wanted to implement your own functionality where you have like the easiest entry point where you can modify existing constraints, you can add new constraints, and you can include new or proprietary data as well. So for our technology capacity targets, we set up a CSV that's in the repository. It'll look something like this with just the header, and then you add in the technology. So for example, we have solar for our planning horizon 2030, for whatever states we want to enforce that constraint over, for the actual carrier, and then our actual value in terms of megawatts. So 8.5 gigawatts, that's as much as we're allowed to invest. So this just sets our build rate for 2030. So we can do this with supply side technologies, but also demand side technologies as well, such as oil furnaces. We want to make sure we don't invest too much or something. Similarly, for EVs, we have our light duty, medium duty, heavy duty, and buses, and we can just enforce different percentages. So this would, for example, be light duty vehicles can only satisfy up to 34% of our total vehicle demand. So we just set build limits on vehicles. You run the model. So you run the model in the same way. You will get a structure that looks like this. And then you can also inspect the network yourself. So you can import the network directly into your Python file and look at the results yourself. And then I'll just quickly go through some of the results here in 2 minutes. In some of these results, from the sector coupling side, one nice thing is you can get these energy flow Sankey graphs. You can see how energy is flowing through your model and like what energy is being rejected and being consumed by each sector. These ones I find very helpful because it allows you to benchmark against other organizations such as the EIA or LLNL who put out very similar graphs. So it's a very powerful validation technique, I think. And you can do the same with carbon as well to see how carbon from like natural gas and coal is flowing through your model. Production, so in the top, we have production by sector. So the top is showing the production from the power sector. The bottom is showing from the residential sector. And for all the different sectors, a pretty standard time series graphs. Same as capacity graphs. So on the top is existing and new, kind of the blue and orange there. And the bottom is residential sector. So again, very standard graphs that just like spat out automatically for you. And then same with natural gas. So you have all these different ones like demand or domestic trade values. The fuel price of natural gas is endogenous to the system, so you can look at that. Yeah. And then just in the conclusion slide, so what did we do? We tried to evaluate regional decarbonization pathways for New England. We set up PyPSA-USA. We implemented some policies such as our technology targets and EV policies, and then we looked at these automated results. What the model doesn't do right now, so it doesn't have these alternative fuel pathways such as hydrogen and biofuels and these kind of things that we have to implement. Our industrial sector, I think there's still a lot of room for improvement. And then this non-road vehicle transportation decarbonization, so air, train, and marine decarbonization pathways. Yeah, that's it. Sorry, I know I sped through that last bit kind of quick. But yeah, that is it. Yeah, I don't know. If there's any questions, please fire them off. Thank you for listening. I appreciate it. And thank you for the questions that already popped up.
Yeah, I guess if I can jump in here.
Please.
How does PyPSA compare to other capacity expansion models or just like electricity system models in general?
Yeah, super question. That's a super question. So, Kamran is definitely the expert. He has a better view of the power system landscape in the USA, but I'll give my take on it. So I think the three kind of big ones that I see floating around in the open source USA atmosphere in the USA is PyPSA, GenX, and Reads. Full disclosure, I've never used GenX or Reads. I've read about them, but never used them. So I can't really speak from a usability perspective. From a data perspective, GenX, it depends on Power Genome. That's their data engine. And I think we pull like very similar data sources like GenX and PyPSA. I think the differentiator between those two is that GenX will kind of put a heavier emphasis on like decomposition techniques and temporal like resampling strategies and whatnot to capture more of like the transition. So instead of these like 10-year gaps, you'll be able to kind of run each year as your master problem, and your operational slave problem will be each year. So it allows you to kind of run more years. Whereas like PyPSA-USA, we kind of more often will run either like hourly resolution or kind of maybe squish like 2 or 3 hours together and just kind of average over them. So you would kind of have heavier emphasis on maybe temporal resolution, but we kind of miss out on trying to model each year in the transition. In terms of reads, I don't know too much about reads. I know from what I've heard, since they have like a big team, they've kind of captured that last like 10% of the data quality better, since they have a team like continually updating it and ensuring that all like asset level data is in there. But yeah, I'm not comfortable like answering like how necessarily the results compare. Like I don't have that info. But those are the three I would like definitely look at. I think they're all like very reputable. Yeah.
Great, thanks. And I don't mean to keep people, but do the other models do the sort of demand side aggregation as much? I'm not as familiar, frankly.
Yeah, so to the best of my knowledge, we're the only model of this that actually import this Temu nodal network. So like the reads zonal boundaries, they come directly from reads. So reads will be based on zones as well. GenX, I believe, is also zonal based, but I don't know. I think they also pull in these reads zonal interface limits, but don't quote me on that. Yeah. Yeah.
Great.
That's
Thank
a
you
good
so much.
question. Yeah, of course.
Any last minute questions for Trevor? Trevor, thank you so much for an amazing hands-on
Of course.
tutorial.
Thank you. Yeah, thank you for having me. I'm sorry the power sector was kind of rough and dirty. Definitely reach out to Kamran if you have questions in it. He will be more than
No, you
happy
did
to
an
answer.
amazing job. Yeah.
Mhm.
That was
Thank you.
awesome. Thank you, Trevor.
Thank you, Jacqueline.
Thanks, everybody.
Thanks, everyone.
Thank you all so much.
Yeah, I appreciate it.
Okay. Thanks. Bye, Trevor. See you.
Yeah. Bye, everyone. Thank you again.
Thank you.